The night sky holds secrets that could reshape our understanding of reality itself. We are exploring 25 interstellar phenomena that challenge everything we think we know about the cosmos. You will gain a new perspective on the universe, discovering how cosmic mysteries from dark energy to quantum entanglement reveal a reality far more intricate than we ever imagined. What if the quiet vastness of space is not empty, but rich with information we are not yet equipped to perceive? Why do the fundamental laws of physics appear so precisely arranged to allow our existence? This journey will deeply change how you see your place in the grand scheme of things. What single cosmic mystery makes you question the nature of reality? The silence of the cosmos is not merely an absence of sound, but a profound puzzle. Given the sheer number of stars and planets, the universe should be teeming with intelligent life, a chorus of cosmic conversations. Yet we are met with a deep and pervasive quiet. This is the heart of the Fermi Paradox, named for physicist Enrico Fermi, who, during a casual conversation in the 1950s, posed a deceptively simple question. Where is everybody? The math suggests they should be here, but the evidence, or rather the complete lack of it, suggests we are profoundly alone. Astronomers like Jill Tarter, who dedicated her career to the search for extraterrestrial intelligence, and the late Stephen Hawking, who pondered the implications of contact, have both wrestled with this cosmic contradiction. One proposed solution is the thought-provoking Great Filter hypothesis. This idea suggests that at some point between the emergence of life and the development of a galaxy-spanning civilization, a barrier arises that is nearly impossible to cross. It could be that life itself is extraordinarily rare, or more soberingly, that intelligent civilizations inevitably reach a point of technological capability that leads to a transition we cannot yet see. Other possibilities are less stark but equally mind-bending. Perhaps advanced beings have moved beyond the primitive radio signals we scan for, communicating through technologies or in dimensions we cannot yet perceive. Maybe they are already here, observing us in a way that is indistinguishable from the natural world. This paradox forces us to question our most human-centered assumptions. We imagine intelligence and technology progressing along a path similar to our own, but what if that is a deeply provincial view? The cosmic silence might be telling us that intelligence is not what we think it is, or that the destiny of technological species is far stranger than we have dared to dream. Contemplating our apparent solitude in the vast galactic arena challenges not just our place in the universe, but our understanding of life, consciousness, and the very trajectory of existence. What fundamental truth about reality is hidden within this great quiet? This sense of cosmic loneliness finds a strange echo in the behavior of space-time itself, a phenomenon that seems to defy the very laws of physics as we know them. Our profound cosmic solitude is mirrored by an equally deep mystery within the very fabric of the cosmos. Galaxies should not be able to hold themselves together. Based on the visible stars and gas we can observe, these vast islands of stars spin at such tremendous speeds that the centrifugal force should fling them into the void. Yet they remain perfectly intact, held together by an invisible gravitational glue. This was the monumental discovery of astronomer Vera Rubin in the 1970s. Her meticulous observations revealed a stark discrepancy. The outer stars of galaxies orbit just as fast as the inner ones, a motion that defied the predictions of Newtonian gravity and implied the presence of a massive, unseen component. This invisible substance, now called dark matter, does not emit, absorb, or reflect any form of light. It is completely transparent to the entire electromagnetic spectrum, making it utterly undetectable by our telescopes. We only know it is there because of its powerful gravitational pull, a ghostly hand shaping the cosmos from the shadows. Astonishingly, this unseen component makes up about 27% of the entire universe, far more than all the ordinary matter, the stuff of stars, planets, and us combined. How do we search for something that is fundamentally invisible? Scientists are pursuing multiple paths. At facilities like the Large Hadron Collider, they are trying to create dark matter particles by smashing ordinary particles together at near light speed, hoping to catch a glimpse of the debris. Deep underground, in abandoned mines shielded from cosmic rays, incredibly sensitive detectors wait for the rare, faint bump of a theoretical dark matter particle, known as a weakly interacting massive particle, or WIMP, passing through. Perhaps the most compelling evidence comes from a cosmic trick of light called gravitational lensing. The immense gravity of dark matter warps the fabric of space-time around it, bending the light from distant galaxies as it travels toward us. We see these background galaxies stretched and distorted into faint arcs and rings, tracing the outline of the invisible dark matter halo. This effect is like seeing the silhouette of a person by the way they distort the light shining through a curtain. Not everyone is convinced that an entirely new form of matter is the answer. Some physicists propose a radical alternative, a modification to the laws of gravity itself, known as modified Newtonian dynamics, or MN. This theory suggests that on the vast, gentle scales of galaxies, gravity behaves differently than we expect, eliminating the need for dark matter. Yet, most evidence, from the cosmic microwave background to the way galaxy clusters interact, continues to point toward an invisible, dominant substance. The existence of dark matter forces a humbling question. What does it say about our standard model of physics, our most complete theory of the fundamental particles and forces, if the vast majority of the universe's matter is made of something it does not include? We are like mapmakers who have only charted a small island, unaware of the vast, dark continent that lies just beyond our sight. This invisible force shaping the cosmos on the largest scales is locked in a cosmic tug-of-war with another, even more dominant power, one that is not pulling matter together but flinging it apart. This invisible cosmic scaffolding, dark matter, is locked in a struggle with an even more dominant and enigmatic force. While dark matter pulls the universe together through gravity, something else is actively pushing it apart, and at an ever-increasing rate. The cosmos is not merely expanding, it is accelerating, a discovery so surprising it reshaped our fundamental models of the universe and earned the Nobel Prize in Physics in 2011. The story of this revelation begins not with complex theories, but with patient observation of stars in their final stages. In 1998, two independent teams of astronomers were studying a specific type of supernova in distant galaxies. These stellar explosions, known as Type 1, a supernova, act as cosmic lighthouses, their predictable brightness allowing scientists to measure vast intergalactic distances with precision. The researchers, including cosmologists like Adam Rees, expected to find that the expansion of the universe was slowing down over time, gradually decelerating under the collective gravitational pull of all the matter within it. Instead, they found the opposite. The most distant supernovae were fainter than their calculated distances predicted, meaning they were much farther away than anyone had thought. The only possible explanation was that the expansion of the universe was not slowing, it was speeding up. Some form of repulsive energy, a pressure inherent to the fabric of space itself, was overwhelming gravity's attractive grip. This mysterious agent was christened dark energy. Today, we understand that dark energy constitutes a staggering 68% of the entire cosmos. It is the majority component of the universe, the dominant player in its evolution, yet we have no idea what it actually is. The leading candidate is something Albert Einstein first proposed, then later set aside: the cosmological constant. This idea suggests that empty space is not truly empty, but holds a constant, low-level energy. As the universe expands and more space comes into existence, this vacuum energy also increases, creating the repulsive force we observe. Other theories propose a dynamic energy field that changes over time, known as quintessence, but the truth is, these are just names for our lack of understanding. The nature of dark energy remains one of the most profound puzzles in all of science. Its implications, however, are crystal clear and utterly transformative for the ultimate fate of the cosmos. This accelerating expansion dictates a cosmic endgame. If dark energy continues to dominate, the universe will likely face a gradual cooling, where galaxies drift apart from one another, stars fade over immense timescales, and the cosmos becomes a cold, dark, and dilute expanse. In a more extreme scenario, if the strength of dark energy increases over time, it could lead to a scenario where the repulsive force becomes so powerful that it separates galaxies, then solar systems, then planets, and finally the very atoms that constitute all matter. The existence of dark energy forces us to confront a deep gap in our understanding. How can our most successful theory of gravity, Einstein's general relativity, which perfectly describes the orbits of planets and the bending of light, be so different on the scale of the entire universe? Does this mean we need a new theory of gravity, or is dark energy pointing toward a completely new type of fundamental force, one that only manifests on the grandest of scales? This mysterious pressure stretching the cosmos finds a strange echo in the chaotic and counterintuitive world of the very small, where particles defy the logic of our everyday reality. While dark energy stretches the cosmos on the grandest scale, the universe performs a different kind of magic in the realm of the impossibly small. Two particles can be born together, linked in a way that makes them forever one system, no matter how far apart they travel. Change the spin of one, and its partner instantly reflects that change, even if it is on the other side of the galaxy. This is quantum entanglement, a phenomenon so unusual that Albert Einstein famously described it as spooky action at a distance. He believed this immediate connection challenged the cosmic speed limit set by his own theory of relativity, the speed of light. For decades, it was a philosophical puzzle, a seeming tension within the otherwise successful theory of quantum mechanics. Then, physicists like Elaine Aspect designed clever experiments to test it. They did not just prove that entanglement was real, they demonstrated that it broke something known as Bell's inequalities. This was a critical result. It showed that the link between entangled particles could not be explained by any local hidden variables, meaning there were no secret instructions or preset conditions arranged when they separated. The particles were not just correlated, they were genuinely interacting in a way that went beyond space. This connection appears to be immediate, an idea that questions our most basic understanding of cause and effect. How can information, or at least influence, seem to move faster than light? The answer may be that it is not moving at all. In the quantum view, the two particles are not separate entities sending messages. They are part of one unified quantum state. The space between them may be an illusion from our everyday perspective. This has deep practical implications. Scientists are now using this unique connection to build quantum computers, which use entangled qubits to perform calculations that would take ordinary computers ages. It also forms the foundation for quantum cryptography, creating codes thought to be unbreakable because any effort to listen in on the communication would disturb the fragile entangled state, notifying the users right away. But what does this mean for the nature of reality itself? The various interpretations of quantum mechanics offer very different answers. The Copenhagen interpretation suggests that particles exist in a cloud of possibility until they are observed, compelling the entangled pair to settle on a state together. The many worlds interpretation proposes that every possible outcome of a quantum event truly happens, branching our reality into countless versions, with the entanglement simply reflecting a deeper link across these parallel worlds. Some physicists even wonder if entanglement is a basic feature of space-time, and that the whole universe might be a vast network of interconnected quantum ties. This idea aligns with the holographic principle, which suggests that all the information in a volume of space is written on its two-dimensional boundary, much like a hologram. In such a view, the seamless connection of entangled particles is not a paradox, but a hint that our three-dimensional reality is a projection from a deeper, interconnected layer. What if the separation we experience every day, the sense of being an individual in a vast, empty space, is the true illusion? Quantum entanglement hints that at the most fundamental level, the universe is deeply, instantly connected. This strange non-locality, where information seems to go beyond space, finds its ultimate test in the most extreme places in the cosmos, the event horizons of black holes. The seamless connection of quantum entanglement confronts its ultimate challenge at the edge of a black hole, a boundary where our understanding of physics breaks down. When any object, a book, or even a single atom crosses a black hole's event horizon, it vanishes from our universe forever. According to Einstein's general relativity, that object is drawn toward an infinitely dense point, its unique identity seemingly erased. Yet quantum mechanics holds a sacred rule: information is never truly destroyed. It can be scrambled, transformed, but never lost. This is the black hole information paradox, a direct conflict between our two most powerful theories of reality. The crisis deepened with Stephen Hawking's revolutionary insight. He realized that black holes are not completely black. Due to quantum effects near the event horizon, they slowly emit a faint glow of radiation. This Hawking radiation carries energy away, causing the black hole to gradually shrink and over immense timescales evaporate entirely. The problem is this: the radiation Hawking first described was purely thermal, a random heat bath containing no information about what fell in. If the black hole evaporates, leaving behind only this featureless radiation, then all the information about every star, planet, and particle it ever consumed appears permanently lost. This apparent violation of quantum law sent shockwaves through theoretical physics. A fierce debate erupted. On one side were those who, like Hawking at the time, believed the information was truly gone, forcing a rewrite of quantum mechanics. On the other were physicists like Leonard Susskind, who argued that information must be preserved. Susskind and others championed the holographic principle, a radical idea suggesting that all the information about what falls into a black hole is not lost inside, but is somehow encoded on its two-dimensional event horizon, like a cosmic fingerprint imprinted on its surface. The information is then slowly and chaotically returned to the universe through the Hawking radiation, scrambled beyond easy recognition but never truly erased. This idea finds a powerful, though abstract, realization in string theory through something called the AD-CFT correspondence. It proposes a perfect duality. A gravitational universe containing black holes can be completely described by a quantum theory living on its boundary without gravity. In this view, a black hole's evaporation is just a transformation of information in the boundary theory, a process where nothing is lost. Yet, even this elegant solution creates new puzzles. If information is leaking out from the event horizon, what does that mean for someone falling in? This leads to the intense firewall paradox. Does a barrier of blazing high-energy particles form just inside the event horizon, transforming any astronaut who crosses it to protect the purity of quantum information? Or does space-time remain smooth as Einstein's theory demands, requiring us to rethink how information escapes? This paradox forces us to ask what is more fundamental: the smooth geometry of space-time or the bits of quantum information that describe it. Perhaps space and time themselves emerge from a vast, interconnected network of quantum data. The resolution of this decades-long struggle will likely reveal the path to a unified theory of quantum gravity, showing us how the fabric of reality is truly woven. These singularities of infinite density are not the only cosmic engines warping the universe in impossible ways. The incredible density of a black hole finds a slightly less extreme, yet equally fascinating, cousin in the neutron star. Imagine an object with the entire mass of our Sun, compressed into a sphere no larger than a city. This is the remaining core of a giant star that exhausted its fuel and underwent a supernova event, pushing matter into states so extreme they defy earthly logic. A single teaspoon of this material would weigh billions of tons, a density so immense that the very atoms are transformed. Under this unbelievable pressure, electrons are drawn into atomic nuclei, combining with protons to create a solid ball of neutrons. This cosmic object is a natural laboratory for physics at the breaking point. The first hint of their existence came not from a steady glow, but from a rhythmic pulse. In 1967, a young researcher named Jocelyn Bell Burnell was analyzing data from a radio telescope when she noticed a strange, perfectly regular signal repeating every 1.337 seconds. It was so precise that she and her colleagues humorously labeled it LGM for Little Green Men, briefly considering an artificial source. This discovery, which we now call a pulsar, was in fact a rapidly spinning neutron star. Like a cosmic lighthouse, its powerful magnetic fields channel radiation into beams that sweep across space, and if one of those beams happens to point toward Earth, we observe a pulse with every rotation. These celestial metronomes can spin hundreds of times per second, their stability rivaling that of atomic clocks. But the interior of a neutron star is where the true mysteries lie. At its core, the density may be so great that even neutrons can no longer hold their structure. They may break down into a soup of their constituent parts, quarks and gluons, creating a state of matter known as quark matter. Some theories even suggest the formation of strange matter, a stable substance made of up, down, and strange quarks, which could theoretically transform any ordinary matter it touches. We cannot create these pressures in any laboratory on Earth, so neutron stars are our only window into this exotic physics, challenging our understanding of the strong nuclear force that binds the universe together at its most fundamental level. Recently, a new way of observing these objects has opened up. When two neutron stars spiral inward and finally merge, they create ripples in the fabric of space-time. In 2017, the LIGO and Virgo gravitational wave detectors felt these tremors, and telescopes around the world saw the corresponding flash of light. This multi-messenger astronomy provided a wealth of data, confirming that such cosmic encounters are the forges where heavy elements like gold and platinum are created. These events also offer a direct probe into the extreme conditions of the merger, helping scientists understand the equation of state that governs matter at these incredible densities. Another enigmatic signal from the depths of space may be connected to the most magnetic members of the neutron star family, the magnetars. These objects possess magnetic fields so powerful they could erase a credit card from halfway to the moon. Occasionally, a magnetar can experience a starquake, a sudden shift of its rigid crust, which releases a colossal burst of energy. Many astronomers now believe that at least some of the mysterious fast radio bursts, those incredibly bright and fleeting millisecond flashes of radio waves from distant galaxies, originate from these hypermagnetic neutron stars. The sheer power of these bursts is staggering, often releasing more energy in a thousandth of a second than our Sun does in an entire day. What can these cosmic extremes, where matter is pushed to its absolute limit, teach us about the fundamental forces that govern our universe? They are natural experiments testing the laws of physics under conditions we can only dream of recreating. They show us the incredible resilience and strangeness of matter and hint at entirely new phases of existence hidden within their cores. The dense, dynamic lives of neutron stars stand in stark contrast to the vast, quiet expanses that separate them, a cosmic emptiness that is not truly empty at all. Our own galaxy is not merely drifting, it is being pulled. The Milky Way, along with thousands of neighboring galaxies, is caught in a vast cosmic river, all flowing toward a single, unseen point in the darkness. This mysterious destination is known as the Great Attractor, a gravitational anomaly of staggering proportions located in the direction of the constellations Centaurus and Norma. Its existence was first uncovered not by seeing it, but by mapping the motion of everything around it. In the 1970s and 80s, astronomers studying the cosmic microwave background, the faint afterglow of the Big Bang, noticed a curious dipole anisotropy. The radiation appears slightly warmer in one direction of the sky and cooler in the opposite direction, a telltale sign that our local cluster of galaxies is moving at an incredible speed relative to this primordial backdrop. Large-scale surveys of galaxy motions confirmed this flow, revealing a coherent stream of thousands of galaxies all heading toward the same invisible gravitational center. The central mystery of the Great Attractor is compounded by its location. It lies directly behind the plane of our own Milky Way, in a region astronomers call the zone of avoidance. Here, the dense clouds of gas and dust, along with the brilliant stars of the galactic central bulge, create a near-impenetrable veil for optical telescopes. It is like trying to see a distant mountain range through a thick, dusty fog. To peer through this cosmic obstruction, scientists have turned to other wavelengths of light. Using powerful radio telescopes like the Parkes Observatory in Australia and infrared telescopes that can cut through the dust, astronomers have begun to map the hidden structures behind our galaxy's core. What they have found is not one single colossal object, but an immense concentration of mass known as the Norma cluster, which itself is part of an even larger supercluster, the Laniakea supercluster. This discovery redefined our cosmic address, showing that the Milky Way is merely an outlying suburb of a vast continent of galaxies, all gravitationally bound to the Great Attractor at its heart. But what is the source of this immense pull? The visible mass of the galaxies in the Norma cluster and the surrounding Laniakea supercluster is substantial, but calculations suggest it is still not enough to account for the full strength of the observed flow. This points toward the dominant hand of dark matter. The Great Attractor may be the gravitational signature of an extraordinarily dense knot in the cosmic web of dark matter, a node where the invisible scaffolding of the universe has gathered into a deep well of gravity, pulling everything in its vicinity toward it. This motion is part of an even grander journey. Our flow toward the Great Attractor is itself just a small part of a larger current, as the entire Laniakea supercluster is being pulled toward an even more massive concentration of mass billions of light years away, known as the Shapley Attractor. We are caught in a cosmic hierarchy of flows, a river within a river. What does this relentless pull reveal about the large-scale structure of the universe? It shows us that the cosmos is not a uniform expanse, but a dynamic tapestry of gravitational landscapes, with mountains and valleys of mass that guide the motion of galaxies over billions of years. The immense gravitational pull of this unseen attractor finds its perfect cosmic counterpoint in the vast, empty expanses that stretch between these nodes of the cosmic web. The same gravitational landscape that pulls galaxies toward the Great Attractor also contains regions of profound emptiness. In the constellation Eridanus, there exists a cosmic desert so vast it defies easy comprehension. The Eridanus Supervoid spans an almost unimaginable 1.8 billion light-years, a bubble of near-nothingness containing far fewer galaxies than any model of the universe predicted. This is not merely an empty patch of space, but a gaping hole in the large-scale structure of the cosmos. Its discovery was intertwined with another long-standing mystery. For years, maps of the cosmic microwave background, the ancient light from the infancy of the universe, showed a prominent and puzzling cold spot, a region significantly cooler than its surroundings. Data from the Planck satellite and other observatories revealed a stunning correlation. This cold spot on the sky aligns almost perfectly with the location of the Eridanus Supervoid. It appears we are looking at a single, colossal phenomenon. But how could an empty region of space make the afterglow of the Big Bang appear colder? The leading explanation involves a subtle relativistic effect known as the integrated Sachs-Wolf effect. As photons from the cosmic microwave background travel across the universe, they must climb in and out of the gravitational wells created by concentrations of matter. Normally, the energy a photon loses climbing into a well is regained when it climbs out. However, in an expanding universe dominated by dark energy, the gravitational wells of large-scale structures actually decay over time. A photon entering a supervoid loses energy as it climbs out of the shallow potential, but it does not regain all that energy because the void itself has become deeper during the photon's long journey. The net result is that the photon loses a tiny amount of energy, shifting it to a slightly colder temperature. Over the immense breadth of the Eridanus Supervoid, this tiny effect adds up, creating the observed cold spot. Researchers like István Sapudi have studied the statistical significance of this pairing, noting that such a large void is a rare, though not entirely impossible, occurrence in our standard model of cosmology. Yet its sheer scale continues to challenge our understanding. How did such an immense region of emptiness form in the relatively short time since the Big Bang? The processes of gravitational collapse that built galaxies and clusters seem insufficient to have cleared out such a volume so completely. This has led to more exotic proposals. Some theorists suggest the void could be the imprint of a cosmic texture, a kind of structural feature in the fabric of space-time left over from the universe's early phase transitions. Others, pushing the boundaries of physics, have even proposed that the cold spot could be evidence of an interaction with another domain in a wider multiverse, a subtle mark on our cosmos from a presence we cannot directly see. The existence of the Eridanus Supervoid forces a fundamental question. Are the initial conditions that seeded all cosmic structure more complex and varied than our models allow? This vast emptiness stands in stark contrast to the next cosmic mystery, where the universe appears not empty but impossibly organized. From the vast emptiness of a supervoid, we turn to a structure of almost impossible density and scale. Stretching across an astonishing 10 billion light-years, the Hercules-Corona Borealis Great Wall is a cosmic formation so immense it seems to defy a foundational rule of the universe. This rule, known as the cosmological principle, states that when you look at the universe on a sufficiently large scale, it should appear roughly the same everywhere, smooth and uniform, with no single region standing out as special. The existence of this gargantuan wall of galaxies directly questions that assumption. Its discovery did not come from a traditional star map, but from a survey of the most energetic events in the cosmos. A team of astronomers led by István Horváth was analyzing data from gamma-ray bursts, the brilliant flashes signaling the end phases of massive stars or the merging of dense cosmic objects. These bursts act as brilliant beacons illuminating the galaxies they reside in. When the team mapped the locations of these events, they noticed a startling concentration, a thick band of galaxies clustered together in a structure far larger than anyone thought possible. Standard cosmological models had suggested a theoretical upper limit to how big cosmic structures could grow, a limit the Great Wall surpasses with ease. How could something this vast form in the time since the Big Bang? The gravitational influence of dark matter is the primary architect of cosmic structure, drawing ordinary matter into web-like filaments and dense clusters. For a wall of this magnitude to exist, it implies an initial seed of extraordinary density in the primordial universe, a significant region in the early cosmic landscape that was substantial enough to gather this incredible collection of galaxies through billions of years of gravitational growth. Does its existence mean the early universe was not as smooth as we believe, dotted with giant variations that grew into these colossal walls? Or does it point to a need to refine our understanding of dark matter and gravity itself, perhaps on scales so grand our current physics is incomplete? The Hercules-Corona Borealis Great Wall stands as a monumental challenge, a reminder that the universe may not play by the simple, uniform rules we have assigned to it. This contemplation of cosmic scale and fundamental structure naturally leads us to wonder about the delicate balance of the forces that allowed such a universe to even exist. The delicate balance of forces that built the Hercules-Corona Borealis Great Wall is echoed in a far more intimate cosmic mystery, one written into the very laws of physics. The universe appears perfectly calibrated for life. Alter any of the fundamental constants by a hair's breadth, and the cosmos as we know it would vanish. This is the fine-tuning problem. The strength of gravity is a prime example. If it were even slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, matter would never have clumped together to form stars and galaxies. The cosmological constant, which governs the acceleration of the universe's expansion, is fine-tuned to an even more astonishing degree. Its observed value is 120 orders of magnitude smaller than what quantum field theory predicts. It is as if you aimed for a target 1 centimeter wide and missed by a distance greater than the entire observable universe. Similarly, the strong nuclear force which binds atomic nuclei together has a very specific strength. Make it a few % stronger, and all the hydrogen in the early universe would have fused into helium, leaving no water or fuel for stars. Make it slightly weaker, and heavy elements essential for planets and life would never form. Physicist Martin Rees explored this profound cosmic coincidence in his book Just 6 Numbers, illustrating how our existence hinges on a razor's edge. How can we explain this seemingly miraculous setup? One proposed answer is the anthropic principle. In its simplest form, it suggests that we can only observe a universe capable of supporting life because we are here to observe it. It is a selection effect. We should not be surprised to find ourselves in a habitable cosmos, any more than a fish is surprised to find itself in water. For many, this is an unsatisfyingly circular answer. A more expansive solution is the multiverse hypothesis. This idea posits that our universe is just one bubble in a vast cosmic foam of universes, each with its own unique, randomly determined physical constants and laws. In this infinite ensemble, most universes are sterile and stillborn, but by sheer chance, a tiny fraction, like our own, possess the right combination for complexity and life. We do not live in a special universe, we simply live in one of the rare ones that allows our existence. Other thinkers propose that the constants are not random at all, but are the inevitable outcome of a deeper, unified theory of physics that we have not yet discovered. Perhaps these numbers are the only possible values that allow a logically consistent cosmos to exist. The fine-tuning problem forces a deeply philosophical question. Does this apparent cosmic design point toward a deeper level of physical reality, or does it hint at something more? The search for an answer leads us to particles that, by all rights, should not exist at all. A single, powerful signal once pierced the cosmic silence, and for 72 seconds it seemed to speak. On August 15, 1977, astronomer Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University when his eye caught a sequence of numbers and letters so extraordinary he circled it and wrote one word in the margin. Wow, the signal was not a message we could decode, but its characteristics were precisely what scientists had predicted for an artificial transmission from the stars. It appeared in a narrow, quiet band of the radio spectrum, a band where natural cosmic noise is minimal, making it an ideal channel for interstellar communication. It was incredibly intense, 30 times louder than the background static of deep space. Most importantly, it followed the exact pattern a signal from a fixed point in space would make as the Earth's rotation swept the telescope's field of view across it. It rose in intensity for 36 seconds, peaked perfectly, and then fell away for another 36 seconds, a perfect bell curve written in radio waves. Amon himself reflected on the profound nature of the find, noting that nothing so compelling has ever been found since. The search for a repeat signal became an ongoing focus, with Amon and others pointing telescopes at that same spot in the constellation Sagittarius for decades, but the silence has remained unbroken. The hunt for a natural explanation has proven equally difficult. Some suggested it was a reflection from a piece of human space debris, but the frequency used was internationally protected, reserved for radio astronomy and forbidden for terrestrial transmissions. More recently, a proposal pointed to a passing comet, but the comets in question were not in the telescope's field of view at that precise moment. Each potential solution introduces more questions than it answers, leaving the WOW signal as a perfect, singular enigma. Its legacy is one of profound scientific curiosity. A one-off detection is impossible to verify, a fleeting impression in the cosmic record that cannot be summoned for a second look. It represents both the ultimate hope and the central challenge of the search for extraterrestrial intelligence. Are we listening for a civilization that broadcasts for only an instant, or was this a glimpse of an astrophysical engine we have not yet classified, a natural process that can mimic intelligence with such precision? This solitary shout from the void finds its modern parallel not in a single cry, but in a chorus of repeating cosmic messages that are equally baffling. These fleeting cosmic whispers pack an impossible punch. In just a few thousandths of a second, a single fast radio burst can release more energy than our sun will emit over 80 years. They flash into existence from the deep void and are gone before you can blink, leaving behind only a brief, brilliant screech across radio telescopes. The first one was not even seen in real time. It was discovered in 2007, hidden within 6-year-old archived data from the Parkes Observatory in Australia. Astronomer Duncan Lorimer and his student David Narkevic found a signal so intense and so brief that it defied all known classifications. For years, it was a solitary oddity, a cosmic flash in the pan that many dismissed as an instrumental glitch. Then we found more, and then we found one that came back. This changed everything. We now know there are two distinct types of bursts. The majority are one-off events, a single tremendous shout from a source that then falls silent forever. But a small, fascinating fraction are repeaters, bursting again and again from the same patch of sky, like a cosmic alarm clock with no set schedule. Facilities like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have been revolutionary, detecting hundreds of these events and painting a much richer picture of their diversity. But what cosmic engine could possibly be this powerful, this fast, and sometimes this persistent? The leading suspects are magnetars, a type of neutron star with a magnetic field so unimaginably strong it could distort atoms from 500,000 miles away. A starquake on such an object, a sudden cracking of its rigid crust under immense strain, could release a titanic shockwave, rippling through the magnetosphere and unleashing a firestorm of radio waves. Other theories are even more extreme, suggesting bursts from the violent evaporation of primordial black holes or the cataclysmic collisions of dense objects like neutron stars. The sheer energy involved even forces scientists to briefly consider, and then largely set aside, highly speculative technological origins, such as enormous interstellar light sails powered by focused beams from an advanced civilization. While this is not the favored explanation, the fact that it must be contemplated at all shows just how extraordinary these events are. Yet, their mystery also makes them incredibly useful. As these radio waves travel across millions of light years, they pass through diffuse clouds of ionized gas that slow them down very slightly. The higher frequency waves arrive just a fraction of a second before the lower frequencies, an effect called dispersion. By measuring this smear, astronomers can count the total number of electrons the signal has encountered, effectively weighing all the normal matter, the atoms and gas, that lies between us and the burst. For decades, a portion of this ordinary matter had been missing from our cosmic inventory, and fast radio bursts are now helping us find it, acting as cosmic scales for the universe. Each new detection adds a data point, tracing the otherwise invisible web of gas that filaments the cosmos. One burst in particular, known as FRB 1211-2, stands out. It was the first repeater ever pinpointed to a specific location, a tiny, turbulent dwarf galaxy over 3 billion light-years away. This galaxy is actively forming new stars at a ferocious rate and contains a persistent, weaker radio source at its heart, likely a supermassive black hole or a powerful nebula. This chaotic environment suggests that repeating bursts may be born in the most dynamic and extreme stellar nurseries, where massive stars live fast, leave their mark, and create these magnetized remnants. What do these split-second flashes teach us? They are proof that the universe is filled with transient, powerful phenomena operating on timescales we are only beginning to probe. Each burst is a message from an extreme environment, a natural laboratory where matter and magnetism are pushed to limits we cannot recreate. Their fleeting nature stands in stark contrast to cosmic structures of immense stability, objects that have endured for nearly the entire history of time. Some of the oldest objects in our galaxy present a timeline that seems impossible. Nestled within the halo of the Milky Way, globular clusters are dense spheres of hundreds of thousands of ancient stars, shining like cosmic fossils. For decades, astronomers calculated the ages of these clusters by studying the precise point where stars exhaust the hydrogen in their cores and begin to leave the main sequence, a milestone known as the main sequence turnoff. The faintness and color of this turn-off point act as a reliable clock. When they applied this method, a startling paradox emerged. Some of these clusters appeared to be over 15 billion years old, a figure that directly contradicted the best estimates for the age of the universe itself, which at the time were calculated to be only around 12 billion years. We were faced with a universe seemingly younger than the stars it contained, a profound chronological crisis. This conflict forced a meticulous refinement of our cosmic measurements. The Hubble Space Telescope played a pivotal role, providing exquisitely precise data on the distances and brightness of stars within these clusters. By observing the faint, cooling white dwarfs, the stellar embers at the end of a star's life, astronomers could cross-check the ages derived from the main sequence turnoff. A white dwarf has no internal energy source, so it simply cools and fades at a predictable rate. The oldest, dimmest white dwarfs in a cluster therefore set a firm lower limit on its age. This independent clock helped calibrate the stellar models. Simultaneously, our measurement of the universe's expansion rate, the Hubble constant, was being refined. Projects like the Hubble Key project significantly narrowed the value, leading to a more precise calculation of the cosmos's age, now estimated at about 13.8 billion years. While this new cosmic timeline resolved the most extreme versions of the paradox, a subtle tension remains. The very oldest globular clusters are still dated to around 13.5 billion years, meaning the first generations of stars in our galaxy coalesced when the universe was only a few 100 million years old, an incredibly short time for such complex structures to form. This pushes our models of both stellar evolution and cosmic infancy to their limits. What if our understanding of the internal mixing processes within the very first stars is incomplete? Could their primordial composition, lacking in heavy elements, have altered their life cycles in ways we have not fully accounted for? Or does this rapid formation hint that the early universe provided conditions for star birth that were far more efficient than anything we see today? The light from these ancient clusters is a messenger from the cosmic dawn, and its story challenges the smoothness of our standard cosmological narrative. It suggests that the first chapters of universal history were written in a bold, rapid script, and that some of the oldest residents of our cosmic neighborhood still hold secrets about the true nature of time and the frantic pace of creation. This glimpse into the universe's earliest structures connects to an even more fundamental question, one written into the very radiation that fills all of space. Even our most trusted cosmic measuring sticks are now giving contradictory readings. This is the heart of the Hubble Tension, a growing crisis in cosmology where two impeccable methods for calculating the universe's expansion rate stubbornly refuse to agree. On one side, we have the view from the beginning. The Planck satellite meticulously mapped the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing the subtle patterns in this ancient light, scientists can extrapolate forward, predicting how fast the universe should be expanding today. This method from the early universe yields a Hubble constant of about 67 kilometers per second per megaparsec. On the other side, we have the view from our local cosmic neighborhood. The SH0ES team, led by Nobel laureate Adam Rees, uses a cosmic distance ladder. They observe pulsating stars called Cepheid variables and type 1 a supernova in nearby galaxies, objects with known intrinsic brightness. By measuring how dim they appear, they can calculate precise distances and thus the current expansion rate. This local measurement consistently gives a faster value, around 73 kilometers per second per megaparsec. The difference seems small, but as both methods have been refined to near perfection over the past decade, the gap has not closed. It has widened into a chasm of statistical significance, a 4 to 5 sigma discrepancy that can no longer be dismissed as simple error. Researchers on both sides have checked and rechecked their work, searching for any overlooked systematic flaw. Members of the Planck collaboration have scrutinized their data for any anomaly in the primordial light, while the SH0ES team has painstakingly calibrated their distance ladder using the Hubble Space Telescope to observe thousands of Cepheids. The tension persists. This is not a mere academic debate. It suggests that our standard model of cosmology, the lambda cold dark matter model, might be incomplete. If the early and late universe measurements do not align, then perhaps something happened in the billions of years between them that our models do not account for. One compelling proposal is early dark energy. This idea posits that a transient form of dark energy existed in the universe's first few 100,000 years, an extra push that subtly altered the conditions imprinted on the cosmic microwave background before vanishing. When we use the Planck data, we are not seeing the pure primordial universe, but one that has already been tweaked by this early force, leading to an incorrect prediction for the present day. Other theorists look to more fundamental changes, such as modifications to Einstein's theory of general relativity on cosmic scales, or revisions to the properties of neutrinos, suggesting these ghostly particles may have unusual interactions or masses. The resolution of this tension promises to be revolutionary. It could be the crack in the door that leads us to new physics, revealing a cosmos more dynamic and complex than our current equations allow. This conflict in our measurements of the present finds a curious parallel in the subtle imperfections of the universe's oldest light. The universe's oldest light holds a subtle imperfection that seems to point in a specific direction. This is the so-called axis of evil, a surprising alignment discovered within the cosmic microwave background that invites us to reconsider a foundational pillar of cosmology. When scientists with the Wilkinson Microwave Anisotropy Probe created the first precise full sky map of this primordial glow, they expected to see a random pattern of hot and cold spots, a universe with no preferred orientation. Instead, they found that the largest scale fluctuations, known as the quadrupole and octupole moments, were not scattered at random. Their warm and cool regions appeared strangely coordinated, lining up along a particular axis that stretches across the cosmos. Even more curiously, this axis seems to align with the plane of our solar system, the ecliptic, and also with the direction of our solar system's journey through space. It is as if the universe's grandest fingerprint is subtly connected to our own local cosmic neighborhood. Later, higher precision data from the Planck satellite mission did not smooth away these curiosities. It confirmed them with even greater certainty. The universe's earliest portrait appears to have a faint but undeniable tilt. For the standard cosmological model, which rests upon the assumption of statistical isotropy, this presents a deep puzzle. The idea that the universe should look the same in every direction on the largest scales is central to our entire understanding of its origin and growth. A preferred direction, a cosmic axis, would invite a profound reconsideration of our textbooks. So what could be behind this unusual signature? The most cautious explanation is that we are seeing an illusion created by foreground interference. Perhaps the gentle glow of dust within our own Milky Way, or the distant Kuiper belt of icy objects at the edge of our solar system, is leaving a mark that we interpret as a feature of the ancient universe. Yet, careful efforts to account for these local foregrounds have so far not removed the alignment. This has inspired more expansive ideas. Could it be a clue about the overall shape or topology of the universe? Perhaps space is not infinite and flat, but has a complex, interconnected form, like a hall of mirrors on a cosmic scale, and the axis of evil is a reflection of that grand geometry. Some thinkers even look to physics before the Big Bang, suggesting that the alignment could be a remnant of an earlier phase of cosmic existence, a subtle impression left on our universe from a prior state. If this axis is confirmed to be real and fundamental, the implications are profound. It would mean the universe has a built-in directionality, a cosmic reference that breaks a fundamental symmetry we have long taken for granted. Our place in the cosmos, often thought to be entirely random and modest, might hold a quiet, mysterious connection to the largest scales of reality. This search for hidden patterns in the fabric of the cosmos finds its deepest expression in the quest to hear the faintest echoes from the dawn of time. Even the most familiar building blocks of matter can hide profound secrets. The proton, a fundamental component of every atom, has become the center of a deep puzzle that questions the very precision of our physical laws. This is the proton radius puzzle. For decades, the proton's charge radius, a measure of how its positive charge is spread out, was considered a well-known quantity, measured by bouncing electrons off it or studying the light emitted by hydrogen atoms. Then, around 2010, a team at the Paul Scherrer Institute in Switzerland performed a radically different experiment. They created an exotic form of atom called muonic hydrogen. Instead of an electron orbiting the proton, they used a muon, a particle 200 times heavier but otherwise identical to an electron. The heavier muon orbits much closer to the proton, acting as a far more sensitive probe of its size. By measuring the precise energy levels of this muonic atom with exquisite accuracy, the researchers calculated the proton's charge radius. The result was surprising. The proton measured about 4% smaller than the value obtained from decades of regular hydrogen experiments. This was not a minor statistical fluctuation. It was a significant discrepancy that shook the foundations of particle physics. The teams at institutions like the Max Planck Institute, who had refined the measurements with regular hydrogen, were equally confident in their results. This meant one of two things. Either there was a hidden, systematic error in one of the most precise experimental methods ever devised, or our most successful physical theory, quantum electrodynamics, was incomplete. Quantum electrodynamics describes how light and matter interact with breathtaking accuracy, and it had passed every test for decades. The proton radius puzzle presented a direct challenge. If the theory is correct, the proton's size should be the same no matter what particle is orbiting it. The fact that the measurements disagreed suggested that the presence of the heavy muon might be revealing a new interaction or force that does not affect the lighter electron. This puzzle connects to other anomalies in precision physics, most notably the muon G-2 anomaly, where the magnetic properties of the muon itself also deviate slightly from theoretical predictions. Together, these discrepancies form a compelling pattern. They hint that there may be unknown particles or forces lurking just beyond the sensitivity of our current particle colliders, subtly influencing the behavior of matter. What does this mean for the Standard Model? It suggests that this incredibly successful theory, which describes all known fundamental particles and forces, might be a low-energy approximation of a more complete theory. The proton radius puzzle is a tiny crack in a magnificent structure, but through that crack, we might glimpse an entirely new layer of reality. The search for answers at this quantum frontier is mirrored by mysteries arriving from the depths of interstellar space, carried by particles of immense energy. The universe constantly sends a silent, invisible rain of atomic fragments toward our planet, moving at nearly the speed of light. These cosmic rays are mostly low-energy protons, but a tiny fraction carry energies so immense they challenge our understanding of natural accelerators. In 1966, physicists Kenneth Greisen, George A. Zatsepin, and Vadim Kuzmin calculated a fundamental limit for this cosmic flow. They proposed that the space between galaxies is not truly empty, but filled with the faint afterglow of the Big Bang, known as the cosmic microwave background radiation. A proton journeying for millions of light years from a distant galaxy would inevitably meet these ancient photons. Each encounter would gently reduce the proton's energy, much like a traveler moving through a soft, persistent mist. The Greisen-Zatsepin-Kuzmin cutoff, often called the GZK cutoff, suggested that cosmic rays from sources beyond our local supercluster should lose energy over time, falling below a certain threshold long before they reach us. It appeared to be an unbreakable cosmic rule, yet our detectors tell another story. Observatories like the wide-ranging Pierre Auger array in Argentina, which uses thousands of water tanks to observe the brief atmospheric showers created when these particles arrive, have repeatedly recorded cosmic rays with energies far beyond the expected limit. These are not just slightly over the line, they carry energies millions of times greater than anything we can produce in our most advanced particle colliders. The mystery grows when we try to trace their origin. Many of these ultra-high energy events seem to arrive from directions outside our local galactic neighborhood, from the vast extragalactic expanse. How did they travel so far with so much energy preserved? One idea is that they come not from the distant universe, but from relatively nearby sources within a few 100 million light years, where the gradual energy loss from the cosmic background is less intense. The puzzle is that we do not see clear, enormous astrophysical sources in those regions capable of such powerful acceleration. Another, more exciting possibility is that our grasp of particle physics itself is still evolving. Perhaps unknown processes are at work in these extreme settings, mechanisms that can push particles to energies we once thought nature did not allow. Or maybe these cosmic rays are not protons at all, but heavier atomic nuclei like iron, which interact with the background radiation differently and might journey farther without losing all their strength. This question connects to one of the most remarkable observations in cosmic ray science, often called the "Oh my God" particle, detected in 1991 by the Fly's Eye instrument in Utah. This single subatomic particle carried the kinetic energy of a well-thrown baseball, all contained within one invisible speck. It was an event so unexpected that it prompted a full rethinking of the high-energy universe. What kind of cosmic event could possibly create such an extraordinary messenger? The candidates include the most energetic phenomena we know, such as active galactic nuclei with their supermassive black holes, or the immense jets from gamma-ray bursts. Still, even these extreme sources struggle to account for the energies we observe. The ongoing detection of particles beyond the GZK cutoff clearly shows that the universe contains accelerators of a scale and power we have not yet fully envisioned. Each one that meets our atmosphere is an emissary from a hidden realm of immense energy, carrying coded clues about the fundamental laws that govern matter under conditions we could never reproduce on Earth. They mark the absolute high-energy frontier, inviting us to wonder what other limits we have imagined for the cosmos might simply be steps in our journey of discovery. Even our cosmic accounting books show a staggering shortfall. When we tally all the ordinary matter in the universe, the atoms that make up every star, planet, and galaxy, we come up with a puzzle. The amount of matter predicted to exist by two of our most trusted cosmic measurements, the cosmic microwave background and the theory of Big Bang nucleosynthesis, is about twice as much as we can actually see. Half of all the normal matter in the cosmos is simply unaccounted for. This is the missing Baryon problem, a cosmological case of misplaced inventory on the grandest possible scale. We can see where the matter should be, but our telescopes find only empty space. So where did it all go? The leading suspect is a ghostly, diffuse web of gas known as the warm-hot intergalactic medium. This is not a cloud of cold hydrogen, but a superheated plasma, a thin soup of protons and electrons with temperatures ranging from hundreds of thousands to millions of degrees. Gas this hot does not emit the kind of visible light our telescopes are designed to catch. It is a cosmic fog, invisible to most of our instruments, yet it is thought to weave through the vast voids between galaxies, tracing the invisible dark matter filaments of the cosmic web. How do you find something that refuses to be seen? Astronomers have turned to clever indirect methods. One involves using the cosmic microwave background itself as a backlight. When this ancient light passes through a cloud of this hot, ionized gas, electrons within the cloud can scatter the photons, giving them a tiny boost in energy. This subtle effect, known as the Sunyaev-Zeldovich effect, creates a specific, faint shadow in the microwave background, a cold spot that allows us to map the location of these otherwise invisible gas clouds. Another technique uses bright quasars as distant lighthouses. As the light from a quasar travels through the cosmic web toward us, atoms in the warm, hot intergalactic medium absorb specific wavelengths, imprinting a complex barcode of absorption lines on the quasar's spectrum. By decoding this barcode, scientists can identify the composition, temperature, and density of the hidden material the light has passed through. Finding these missing baryons is crucial for more than just balancing our cosmic budget. Their existence and distribution hold the key to understanding how the large-scale structure of the universe formed. This warm, hot intergalactic medium is the reservoir from which galaxies grew and the environment that continues to influence their evolution. It is the final piece of the ordinary matter puzzle, and its confirmation would mean our standard model of cosmology is essentially correct about the inventory of the cosmos, even if we cannot directly see all of it. The next generation of X-ray observatories, like the European Space Agency's Athena mission, are being designed specifically to detect the faint, high-energy glow of this superheated gas. They will act as cosmic thermometers, finally allowing us to take the temperature of the voids and trace the complete skeleton of the cosmic web. The fact that we have such difficulty accounting for the very stuff we are made of is a profound lesson in humility. It suggests that the universe is far more effective at hiding things in plain sight than we ever imagined. This search for our universe's missing atoms finds a deeper, more fundamental counterpart in a question about its very first moments, a time when matter itself was almost entirely transformed. Our universe should not be here. In the first moments of the Big Bang, energy should have condensed into perfectly equal amounts of matter and antimatter. For every proton born, an antiproton should have emerged. For every electron, a positron. And according to all our known laws of physics, these pairs of particles and antiparticles should have immediately annihilated each other upon contact, converting their mass back into a burst of pure radiation. The entire cosmic story would have ended almost as soon as it began, leaving behind a lifeless, featureless sea of light. And yet, here we are, in a cosmos filled with galaxies, stars, planets, and life. Something tipped the scales. An infinitesimal imbalance, a 1 in a billion asymmetry, allowed a tiny surplus of matter to survive that mutual destruction. All the stars and galaxies we see are made from that fragile, leftover scrap. This is the Baryon asymmetry puzzle, and it is one of the most fundamental questions in all of science. The Russian physicist and Nobel laureate Andrei Sakharov first outlined the 3 essential conditions needed for our matter-dominated universe to emerge. He proposed that the early universe must have experienced a departure from thermal equilibrium, a process that violated the conservation of baryon number, and most crucially, a fundamental breakdown of symmetry between particles and antiparticles known as CP violation. CP violation means that the laws of physics treat matter and antimatter slightly differently, creating a tiny preference for one over the other. We have observed a small amount of CP violation in the decays of certain exotic particles like kaons and B mesons, studied at particle accelerators like the Large Hadron Collider. But the effect is far too weak to account for the overwhelming dominance of matter we see in the cosmos today. It is as if we have found a single drop of water, but need to explain an entire ocean. This has driven physicists to propose more dramatic mechanisms that could have operated in the universe's first fractions of a second. One leading idea is electroweak baryogenesis, which suggests that as the fundamental forces of nature separated during the early cosmic expansion, a phase transition occurred, like water freezing into ice. Bubbles of the new phase of the universe expanded, and at their walls, the conditions were just right for Sakharov's principles to create a matter surplus. Another compelling theory is leptogenesis. This proposes that very heavy, sterile neutrinos decayed in the early universe, and in doing so, they violated CP symmetry, creating an excess of ordinary neutrinos over antineutrinos. Through a subtle interplay of particle interactions, this lepton asymmetry was then converted into the Baryon asymmetry we see today in protons and neutrons. This elegant idea directly ties the fate of matter to the mysterious properties of neutrinos, those ghostly particles that barely interact with the rest of creation. Looking back even earlier to an era of grand unified theories, the imbalance might have been forged when the strong nuclear force split from the electroweak force. At these incredible energy scales, protons themselves are not stable and can decay, a process that could have inherently favored matter over antimatter. The profound implication of all this is that our entire existence hinges on a broken symmetry. We are the children of a cosmic imperfection. Without this one in a billion divergence from perfect balance, there would be no atoms, no chemistry, no planets, and no one to ask why the universe is the way it is. Solving this puzzle would do more than just complete a chapter in a textbook. It would reveal the precise conditions and laws that govern the universe in its very first moments, telling us why there is something rather than nothing. The search for answers now focuses on the most elusive of particles, neutrinos, whose strange oscillations might yet hold the key to the universe's original preference for matter. This deep asymmetry between matter and antimatter finds a strange and perfect mirror in a different kind of symmetry, one that should be broken but is not. The strong nuclear force which glues quarks together to form protons and neutrons possesses a puzzling mathematical perfection. The theory that describes it, quantum chromodynamics, naturally allows for a certain type of asymmetry known as CP violation to occur within its interactions. We know this asymmetry exists in the weak nuclear force, and it is crucial for our universe of matter. Yet, when we look at the strong force, this expected asymmetry is completely absent. It is as if a door that should be wide open is found to be not just closed but perfectly, immovably sealed shut. This is the strong CP problem, and for physicists, it is a profound aesthetic flaw in the otherwise successful Standard Model. The universe seems to be preserving a symmetry for no discernible reason, a fine-tuning so precise it feels unnatural. How do we know this symmetry is there? The most powerful evidence comes from the neutron itself. If the strong force violated CP symmetry, the neutron would be expected to have a slight separation of its positive and negative charges, creating a tiny but measurable electric dipole moment. Think of a perfectly round sphere versus one that is ever so slightly elongated, with a positive end and a negative end. Experiments have hunted for this elongation with incredible precision, measuring the neutron's shape to a level of accuracy akin to determining the width of a human hair from a distance of 1,000 miles. The result, the neutron's electric dipole moment, is perfectly consistent with zero. The strong force is perfectly symmetric, and we have no good explanation for why. To resolve this unsatisfying puzzle, physicists Roberto Pexi and Helen Quinn proposed an elegant solution. They suggested that this perfect symmetry is not fundamental, but is actually the result of a new, dynamic field that pervades the universe. This field would naturally adjust itself to cancel out any CP-violating effects in the strong force, forcing the neutron to remain perfectly round. A consequence of this mechanism is the prediction of a new, incredibly light particle, the action. These actions would be produced in vast numbers throughout cosmic history and would interact only very weakly with ordinary matter, making them nearly invisible. This is where the puzzle takes a thrilling turn. The hypothetical action is now one of the leading candidates for the universe's missing dark matter. A single, elegant idea could therefore solve two of the greatest mysteries in physics at once. It would explain why the strong force is so perfectly symmetric and simultaneously account for the invisible gravitational glue that holds galaxies together. This has sparked a worldwide hunt for these elusive particles. Experiments like the Action Dark Matter Experiment, or ADMX, use powerful magnetic fields inside resonant cavities to try and convert a passing action into a faint microwave photon. Other searches look for the influence of actions on the light from distant pulsars. The discovery of an action would be a monumental event, revealing a hidden layer of cosmic reality and restoring a sense of mathematical beauty to our fundamental laws. The strong CP problem forces us to ask whether our universe is built on principles of deep elegance, or if the apparent fine-tuning we see is a signpost pointing toward physics we have not yet discovered. This theoretical quest for a hidden particle finds a direct connection to strange behaviors observed in the very hearts of stars. For decades, our own sun seemed to be behaving unexpectedly. Nuclear physics gave us a beautiful and precise recipe for how the sun shines, a process of fusion that should release a specific number of ghostly particles called neutrinos. Yet when scientists built detectors to catch these solar messengers, they consistently found only about a third of the predicted amount. This was the solar neutrino problem, a 30-year period of inquiry that challenged our fundamental understanding of stellar engines. Pioneering work began deep underground in the Homestake Gold Mine in South Dakota. There, physicist Raymond Davis Jr. built a tank filled with 600 tons of dry cleaning fluid. His idea was brilliant in its simplicity. As solar neutrinos passed through this vast volume, a tiny fraction would interact with chlorine atoms, transforming them into radioactive argon. By carefully counting these few atoms each month, Davis could measure the sun's neutrino output. His results, confirmed over many years, were clear. The sun was producing far fewer neutrinos than our models suggested it should. This difference was not a measurement error. Later experiments around the world using different materials like gallium and pure water all told the same story. The sun was not broken, but our understanding of the neutrino itself was profoundly incomplete. The resolution came from a revolutionary discovery. Deep inside the Super Kamiok and detector in Japan, a massive tank of ultra-pure water watched for faint flashes of light created when neutrinos interacted. Meanwhile, the Sudbury Neutrino Observatory in Canada used heavy water to detect neutrinos with even greater precision. Together, these experiments revealed the stunning truth. Neutrinos were not disappearing, they were changing identities. The sun produces only one type, electron neutrinos, but on their 8-minute journey to Earth, these particles oscillate, morphing into two other types, muon and tau neutrinos, which the earlier experiments like Homestake could not detect. When all three types were counted, the total number matched the solar models perfectly. This discovery had a profound consequence. For neutrinos to oscillate, they must have mass, however tiny. This was a monumental breakthrough, as the original standard model of particle physics described neutrinos as massless. The 30-year mystery was not a failure of solar physics, but a doorway to new physics. The resolution of the solar neutrino problem is a masterclass in the scientific process. An apparent contradiction, a stubborn anomaly, did not break our models. It refined them, forcing us to look deeper into the nature of reality and revealing a hidden property of one of the universe's most elusive particles. This historical triumph invites us to consider the cosmic neutrino puzzles that remain. Today, detectors are recording neutrinos from vastly more powerful sources than our Sun, from the hearts of distant galaxies and the aftermath of stellar transformations. These cosmic neutrinos carry energies millions of times greater than their solar cousins, and their origins and behaviors are still shrouded in mystery. Just as the quiet difference from our Sun pointed to a fundamental truth, the messages from these distant, powerful ghosts may be guiding us toward the next revolution in our understanding of the cosmos. Two spacecraft sent to explore the outer planets began to drift off course by a distance no greater than the width of a football field each year. This was the Pioneer Anomaly, a tiny but persistent deceleration detected in the trajectories of the Pioneer 10 and Pioneer 11 probes as they traveled beyond Jupiter. For decades, this minuscule drift, an unexplained pull back toward the Sun, baffled scientists who meticulously analyzed the Doppler shift in the spacecraft's radio signals. The data was clear, yet the reason was completely unknown. How could our most precise navigational tools, which had successfully guided these robotic envoys past gas giants, be so subtly wrong in the empty expanse of deep space? The quest for an answer sparked a fascinating array of theories. Some suggested it was the gentle, unseen push of heat radiating from the spacecraft's own systems. Others proposed more exotic ideas, like a slight modification to the laws of gravity itself, or even the gravitational pull from unseen, diffused dark matter in our solar system. The possibility of a tiny, undetected fuel leak was also seriously considered. This small mystery captured the scientific imagination for so long because it represented a potential crack in our understanding of fundamental physics, a whisper that the rules of the cosmos might be different in the quiet reaches of our own celestial neighborhood. The eventual resolution did not come from rewriting the laws of physics, but from an exhaustive, years-long effort in computer modeling. A team of researchers meticulously reconstructed every conceivable source of heat on the aging probes, from their electrical systems to their radioactive power sources. They discovered that the very heat keeping the spacecraft alive was radiating from their central bodies and, crucially, reflecting off the back of their large dish antennas. This anisotropic or uneven radiation of thermal photons acted like a faint, constant braking force, gently pushing the probes back toward the Sun. The anomaly was not a new force of nature, but the cumulative effect of countless tiny photon pushes, a mundane explanation that had been incredibly difficult to model with perfect accuracy. This episode stands as a masterclass in scientific humility. It exemplifies the critical importance of systematic error analysis, reminding us that before we invoke revolutionary new physics, we must first exhaust every possible ordinary explanation. The resolution of the Pioneer Anomaly now informs our approach to every other cosmic discrepancy, from the precise orbits of other distant probes to the subtle tensions in our measurements of the universe's expansion. It teaches us that the universe often hides its deepest secrets not only in grand, explosive events, but in the patient, quiet accumulation of almost imperceptible details. This solved puzzle within our own solar system, born from the gentle pressure of escaping heat, stands in stark contrast to the gravitational anomalies we observe on a galactic scale, where the invisible hand of dark matter shapes the motion of entire galaxies. Even our own cosmic backyard appears to be a vast and unexpected emptiness. We may be living inside the KBC Void, a proposed underdensity spanning hundreds of millions of light years, a bubble of relative quiet that could reshape our interpretation of the entire cosmos. This local cosmic void was first identified by astronomers Ryan Keenan, Amy Barger, and Lennox Cowie through painstaking analysis of galaxy survey data, which revealed our local supercluster resides in a region with a significantly lower density of galaxies and matter than the cosmic average. This is not a small patch of emptiness, but a staggering spherical underdensity that, if confirmed, places us at the center of a cosmic anomaly of almost unimaginable scale. The potential implications of this are profound, offering an elegant solution to the persistent Hubble tension. If we are situated in a vast underdense region, the local gravitational landscape is different. The weaker gravitational pull in our local void would allow galaxies to flow outward more easily, leading to a faster measured expansion rate here and now. Meanwhile, the cosmic microwave background, which reflects the average density of the entire universe, would naturally predict a slower global expansion rate. The two methods would be measuring different environments, resolving the discrepancy without requiring new physics. This single idea could also explain other subtle cosmological anomalies, tying them together into one coherent picture of a locally underdense universe. Yet, the statistical significance of the KBC void is hotly debated. Is this underdensity a rare but permissible fluctuation within our standard model of cosmology, a chance cosmic lottery ticket that we just happen to hold? Or is its sheer size and our central location within it a sign that something is missing from our models, perhaps pointing toward new physics or a revision of how structure forms on the largest scales? The debate hinges on whether such a large void is likely to occur in a universe that is supposed to be broadly uniform. This directly challenges the cosmological principle, the foundational idea that the universe is homogeneous and isotropic on sufficiently large scales. If the KBC void is real and as significant as it appears, it forces a humbling reconsideration of our place in the cosmos. For centuries, we have moved from seeing ourselves at the center of the universe to accepting a position of cosmic mediocrity on a random planet, orbiting an average star in a typical galaxy. The KBC void turns this idea on its head. It suggests we may, in fact, inhabit a very special place after all, a vast and unusually empty region. This is not a return to a geocentric universe, but a recognition that our local cosmic environment might be statistically special in a way that biases our observations. The gravitational influence of such a profound local emptiness would not only affect the expansion rate we measure, but could also be the driving force behind the mysterious bulk flows that pull our entire local supercluster through space. The gentle tug from this local void connects to the immense currents that guide galaxies across the cosmic web. This faint cosmic temperature difference is our own motion, written across the sky. The cosmic microwave background appears slightly warmer in the direction we are heading and cooler in the direction we are leaving behind, a phenomenon known as the CMB dipole anisotropy. It reveals that our entire solar system is moving through the universe at an astonishing 370 kilometers per second. This is our peculiar velocity, our motion relative to the cosmic rest frame defined by this ancient, pristine light. To uncover the universe's own subtle birthmarks, the intrinsic fluctuations from the Big Bang, scientists must first carefully subtract this overwhelming signature of our own journey. This precise subtraction is what allows the profound symmetry of the cosmic microwave background to emerge, hiding the vibrant evidence of our own rapid transit. But where is this immense current carrying us? This measured motion is not a simple flow. It is the sum of multiple cosmic currents. We are orbiting the center of the Milky Way. Our galaxy, in turn, is being drawn toward the Great Attractor, and the entire Laniakea supercluster is itself flowing toward the even more distant Shapley Attractor. The CMB dipole is the net result of all these motions combined, a precise vector pointing toward our ultimate direction of travel through the cosmos. Yet a subtle mystery remains. Does our measured velocity perfectly match the combined gravitational pull from all the massive structures we have mapped? Some analyses suggest there might be a small, unexplained component, a hint that our inventory of the cosmic web's most massive nodes may still be incomplete. Perhaps an even larger concentration of mass, a supercluster or a dark matter filament we have not yet fully charted, is exerting an additional gentle influence on our local universe. This grand cosmic drift forces a profound shift in perspective. We are not fixed, stationary observers, we are travelers, and this motion subtly colors every observation we make. It means our view of the universe is inherently directional, like looking out the window of a moving train. This fundamental measurement does more than just plot our course. It acts as a precise scale, weighing the total gravitational influence of everything in our cosmic vicinity. By analyzing our motion, we can indirectly map the distribution of both visible and dark matter across hundreds of millions of light years, confirming the existence of the vast gravitational landscapes that make up the cosmic web. What does it mean that our most fundamental view of the universe's birth is forever intertwined with the story of our own motion through its present structure? This understanding of our place within a dynamic, flowing cosmos inevitably leads us to ponder where these currents are ultimately taking us, and what final destination awaits the universe itself. Our journey through cosmic mysteries ultimately brings us to a final, profound question. What is the ultimate fate of everything we see? The destiny of the cosmos hinges on a delicate and ongoing struggle between the relentless push of dark energy and the persistent pull of gravity, a battle whose outcome is still uncertain. Current observations point toward a dominant, though not yet fully understood, dark energy, leading cosmologists to outline three primary scenarios for how the story of our universe might end. The first, and currently most favored, is the Big Freeze, also known as heat death. In this vast, quiet future, the universe continues to expand and accelerate forever. Galaxies will drift apart until each is an isolated island in an ever-cooling, ever-darkening void. All the usable energy in the universe will gradually be exhausted, stars will burn out, and even black holes will slowly fade away over almost unimaginable timescales. The cosmos would approach a state of maximum entropy, a uniform, frigid sea where no more work can be done and no new complexity can arise. It is a quiet, gradual fading of all light and life. A second, more intense possibility is the Big Rip. This scenario depends on the precise nature of dark energy, specifically if its repulsive strength increases over time. If dark energy becomes dominant on every scale, its push would eventually overcome all other forces. First, galaxy clusters would be separated, then individual galaxies. The gravitational bonds holding stars within them would come undone. As the end neared, planetary systems would be pulled apart, and finally, in the last moments, the very atoms and subatomic particles that constitute all matter would be separated. The fabric of space-time itself would be profoundly altered in a final instant. The third classic ending, the Big Crunch, is now considered far less likely given our measurements of cosmic acceleration. In this model, the expansion of the universe would eventually slow, halt, and reverse. A great collapse would begin, with all matter and energy rushing back together into a singular point, a mirror of the Big Bang, potentially setting the stage for a new cycle of creation. While the data strongly disfavors this cyclical model for our own universe, the concept of cosmic rebirth remains a compelling idea in some theoretical frameworks. The key to distinguishing between these fates lies in a single number known as the equation of state parameter for dark energy, often symbolized as W. A value of exactly -1 corresponds to a constant dark energy, leading to the gradual big freeze. A value more negative than -1 points toward the phantom energy that would cause the big rip. Our most precise measurements to date from missions like Planck suggest a value very close to -1, making the big freeze the most probable outcome. Yet, the error bars on these measurements still leave a tiny window open for more dramatic endings. Cosmologists like Lawrence Krauss have reflected on the profound implications of the Big Freeze, a cosmos destined for eternal stillness where the arrow of time itself may lose all meaning in a universe with no more change. Brian Greene often discusses how this cosmic endpoint forces us to confront the transient nature of complexity, and how the very laws that allow for life and consciousness also contain the seeds for its ultimate transition. This contemplation of endings naturally leads to more speculative ideas. Could our universe be just one cycle in an endless series of cosmic expansions and contractions, a concept found in both modern cosmology and ancient philosophies? Or could a quantum fluctuation in the seemingly stable vacuum of space trigger a profound phase transition, a bubble of true vacuum that expands at the speed of light, rewriting the fundamental laws of physics in its wake and effectively transforming our universe as we know it? The fact that we can even pose these questions yet cannot yet answer them with certainty reveals the thrilling frontier of modern cosmology. Our limited knowledge about the universe's ultimate fate is not a failure, but a beacon. It illuminates the profound connection between the largest scales of the cosmos and the most fundamental laws of physics, and it reminds us that the story of the universe is still being written, with its final chapter hidden in the mysterious nature of dark energy. These separate cosmic puzzles begin to interlock like pieces of a single, grander mystery. The ghostly pull of dark matter and the strange rotations of galaxies might not require two different solutions but one. Perhaps the modified gravity theory known as MOND is not a replacement for dark matter, but a clue to its complex behavior, a sign of how this invisible substance interacts with the fabric of space-time in ways we have not yet modeled. Similarly, the spooky connection of quantum entanglement and the effort to understand information near a black hole are likely two sides of the same coin. The holographic principle suggests that entanglement is the fundamental glue that weaves space-time itself together, meaning the information approaching a black hole is never truly inside it, but is instantly mirrored on its surface through a vast web of quantum links. Solving one of these riddles could cause a domino effect, unraveling others. A true understanding of dark energy would not only tell us the universe's ultimate fate, but it could instantly resolve the Hubble tension, revealing that our conflicting measurements are simply different perspectives on the same accelerating cosmos. Theoretical physicist Carlo Rovelli often speaks of reality as a network of relations where particles and forces are defined by their connections to one another. In such a view, these 25 phenomena are not isolated oddities, but different expressions of the underlying relational structure of the cosmos. Lisa Randall has explored how hidden dimensions or new symmetries in nature could provide a common origin for mysteries as diverse as the hierarchy problem in particle physics and the nature of dark matter. The path forward demands a dual approach using both immense new tools and profound new ideas, next-generation observatories like the Vera C. Rubin Observatory and the James Webb Space Telescope will map the dark universe with unprecedented detail, while experiments at colliders like the proposed Future Circular Collider will push the energy frontier, potentially creating particles that have not existed since the first moments of the Big Bang. The ultimate goal is a theory of quantum gravity, a framework that seamlessly blends the vast cosmic scale of general relativity with the fuzzy, probabilistic world of the quantum. Such a theory would not just answer our questions, it would undoubtedly reveal questions we have not yet learned to ask. This interconnected web of cosmic challenges paints a picture of a science on the cusp of a revolution. We are no longer merely collecting anomalies, we are starting to see the outline of the larger puzzle they form, a silhouette of a deeper reality waiting to be discovered. These cosmic riddles, from the quantum scale to the edge of the observable universe, are not simply gaps in a map waiting to be filled. They are fundamental tensions, places where our observations and our most cherished theories pull in opposite directions, each one a potential doorway to revolutionary physics. The common thread weaving through all 25 of these phenomena is their profound ability to dismantle our comfortable assumptions. They compel us to consider that the true nature of reality is far stranger, more interconnected, and more magnificent than we have ever dared to imagine. While definitive answers for many of these mysteries remain just beyond our grasp, their very existence marks a monumental achievement in human thought. We have successfully navigated to the very frontier of knowledge, the precise point where our deepest and most meaningful questions begin. The investigation is a living, breathing endeavor, continuing in laboratories placed deep beneath the surface, with telescopes scanning the skies, and in the quiet spaces of theoretical work across the globe. It is a continuous chain of curiosity, with each generation building upon the hard-won insights of the last, pushing the boundary of understanding a little further. We would love to hear which of these phenomena you find most compelling. Share your thoughts in the comments below and subscribe for more journeys to the frontiers of knowledge. In the end, the greatest mystery may not be any single cosmic oddity, but the remarkable human capacity to ask these profound questions and to tirelessly seek their answers across the vast, silent expanse of space